Hello, this video is brought to you by Masori Corporation, your best partner. In this video, I will continue with the introduction to probability and specifically I will look at the counting techniques. My names are Elias Muwao. Let's start by looking at the trials and outcomes and then later on look at permutations. Okay, so if there are n possible outcomes of each of the r trials of an experiment, then there will be n to the power r possible outcomes in the sample space. Now, we are looking at an experiment where we need to perform multiple or different trials. And each of these trials is an input to determining the total number of observations or outcomes that we will have in the sample space. And for us to be able to know, we also need to know the possible outcomes for each individual trial. For example, in this video, I have used an example of tossing a coin. Suppose that the coin is tossed 5 times. Now, we know that a coin has two outcomes. One is the head and the other one is the tail. In this video, I've used the Zambian coin for a 1 kwacha to show how a coin can will look like. And if you look at this coin, we see that there is one outcome where we have the coat of arms and the other outcome where we have the bird. So when you toss this coin, there's a 50-50 chance of you observing the coat of arms or observing the bird. So now, for this coin, the possible outcomes then will be n to the power r, where r is the number of trials or the number of times that you are tossing this coin. And n is a number of possible outcomes that you can observe on each individual trial. So in this our example, our n is 2 because we know that a coin once tossed can land either head up or tail up. In this case, coat of arm up or the bird up. Now, we are taught from this example that the coin is tossed 5 times, meaning our r is equal to 5. So n is equal to 2 and r is equal to 5. When we substitute n and the value for r in this formula, what we'll have is 2 to the power r 5 will be 2 times 2 times 2 times 2 times 2. And this will give us 32 possible outcomes. Therefore, if we toss a coin 5 times, we are likely to have we are going to have 32 possible outcomes in the sample space. Let's look at an advancement to trials and outcomes. The number of ways of selecting r balls with replacement from a box containing n balls is n to the power r. Again, take note, the r here is simply the number of trials or the number of times that you are selecting balls from a given box. So therefore, if we know how many balls we have in the box, then we will know the possible outcomes for each of the observations. And the r becomes the number of times that we are picking each and every ball from the box with replacement. That is, our n then will be equal to n times n times n and so on, and this will simply be n to the power r, where r is the number of trials or the number of times that you are selecting the balls from the box with replacement. Let's look at another example. Suppose that a box contains 10 balls. In how many ways can we sample 3 balls with replacement? So again, we go back to our formula. We know that for us to know the number of ways of selecting 3 balls, therefore, will be n to the power 3, because r in this case is 3. So we note that we have a total of 10 balls, therefore our n will be 10. And from these 10 balls, we want to select 3 balls. So therefore our r becomes 3. So we want to know in how many ways we can sample 3 balls with replacement from a box containing 10 balls. Okay, so our n is 10 and r is 3, which means we are looking at 10 times 10 times 10, which will give us 1,000 possible ways. Okay, let's now look at permutations. A permutation is an ordered arrangement of a set of objects. Here, we are now looking at a situation where order is of great concern, and therefore we want to sample items without replacement. So we note that if order is very important, then if you have 3 numbers, 1, 2, and 3, these numbers arranged in that order will be different if the arrangement was 3, 2, and 1. So therefore, we must note that order matters in permutations. Because it's an ordered arrangement of a set of objects, A, B, C will not be the same as C, B, A. So order is very important when you are dealing with permutations. The other note here is that objects are drawn without replacement. So once you pick an object, you are not going to put that object back where you picked it from. For example, if you are looking at 10 balls in a box and you're supposed to select 3, then every time you pick a ball will not be replaced back in the box. So once a ball is removed, you remain with 9. You pick another ball, you remain with 8. You pick the third ball, it means you will have remained with 7 balls in the box. Let's look at the rules that can help us understand or operate with permutations. The first rule is that the number of ways of arranging n distinct objects in a row is n factorial. Now, n factorial simply means n times n minus 1 times n minus 2 times n minus 3 and so on up to times 2 times 1. So when we say find 2 factorial, for example, then we are saying 2 times 1. 3 factorial will be 3 times 2 times 1. 4 factorial will be 4 times 3 times 2 times 1. So a number factorial is simply that number multiplied by all other numbers as you get down all the way to 1. Okay, the second rule is that the number of ways of arranging R objects selected from n distinct objects in a row is n factorial divided by n minus r factorial. So here n factorial again is n times n minus 1 times n minus 2 times n minus 3 and so on. And then again here we have n minus r factorial, which is n minus r times n minus r minus 1 times n minus r minus 2 and so on until we reach n minus r plus 1. The third rule is that the number of ways of arranging in a row n objects of which p of one type are alike, q of the second type are alike, and r of the third type are alike and so on is simply n factorial divided by p factorial. So those p's which are alike are also multiplied by q factorial, meaning we are looking at q types which are alike, and then r factorial, we are looking at the type r which are alike. So we get the ratio of n factorial to the product of p factorial, q factorial, and r factorial. Let's look at our first task and see how we can apply counting techniques in solving situations involving chances or probabilities. A bag contains 8 white balls and 3 black balls. 2 balls are drawn at random, one after the other. Okay? If the first ball is replaced, find the probability that the balls are of number 1, different colors, and number 2, same color. Now, for us to be able to handle this question, we must understand what is going on. First, we note that there is replacement, meaning once you pick a ball, that ball must be replaced back so that the total still remains 11, 8 white and 3 black. The other part of the question is asking us to find the probability that the balls are of number 1, different colors, and number 2, same color. And here the balls are picked without replacement, meaning once the ball is picked, there is no replacing that ball back in the box. Let's start with part A, where we allow replacement, and then we want to find the probability that the balls picked are of different colors. Okay, so first thing, let's draw a tree diagram. So we have white. We know that in the box we have 11 balls, 8 are white and 3 are black. So if we add the total balls in a box, we have 11 balls. So there is a possibility that the first ball we pick is white or the first ball we pick is black. Now these balls have been replaced in the box. So if we replace the balls and we pick again, we note also that the second ball can be white, given that earlier it was white, or the second ball can be black, given that the first one was white. And if the first ball picked was black, we can also pick the second one to be white, given that the first was black, or the second one to be black, given that the first was also black. Now, at this point then, we need to understand how these probabilities can be calculated. The probability that the balls are of different colors will be obtained by us following the route where we have different colors. If the first ball was white, then the second ball must be black. And if the first ball was black, then the second ball must be white. Therefore, the probability of us obtaining different colors will be this route. So we go white, black, plus black, white. So therefore, probability of different colors will be equal to the probability that first was white and then second was black, plus probability that first was black and second was white. We can show this because the total number of balls in the box is 11 and 8 are white, 3 are black. Therefore, the probability of us picking the first ball being white will be 8 over 11, and the probability of us picking the first ball being black is 3 over 11. The probability of us picking the second ball being white is 8 over 11 because the ball was replaced, so we still have 11 balls. So it will be 8 over 11, and the probability of us picking a black ball, given that the first one was white, is 3 over 11. The probability of us picking a white ball, given that the first was black, is 8 over 11. And the probability of us picking a black ball, given that the first one was black, is 3 over 11. Now here, we are only concerned with white, black, and black, white. Okay? So therefore, we're saying this will be equal to probability that the first one was white, 8 over 11, times probability that the second one was black given that the first one was white, which is 3 over 11, plus the probability that the first one was black is 3 over 11 times the probability that the second one was white given that the first one was black is 8 over 11. And if we simplify this, what we will have is 24 over 121 plus 24 over 121. Adding these will give us 48 over 121. Therefore, if a bag contains 8 white balls and 3 black balls, and then we draw 2 balls at random, one after the other, if we allow for replacement, and then we need to find the probability that the balls are of different colors, that probability will be 48 over 121. Let's look at the second question, where we need to find the probability that the balls are of the same color. If the balls are of the same color, then we note that if the first ball is white, the second one must also be white. If the first ball is black, the second one must also be black. Therefore, we are following this route, white, white, and black, black. So the probability that the balls are of the same color will be probability that first is white times probability that second is white, plus probability that first is black times probability that second is black. Doing that, we note that probability that first is white is 8 over 11, but because replacement is allowed, so probability that the second one is also white is 8 over 11. Probability that the first one is black is 3 over 11, and because we are allowing replacement, probability that the second one is also black is 3 over 11. Simplifying this will give us 64 over 121 for the probability of white, white, plus 9 over 121 probability of black, black. Adding the two gives us 73 over 121. Therefore, if a bag contains 8 white balls and 3 black balls, then we draw 2 balls at random, one after the other. The probability that the balls are of the same color, allowing for replacement, will be 73 over 121. Let's look at part B of the question. Part B is now looking at a situation where replacement is not allowed. If we do not replace the ball after picking, then we note that the first instance, when you draw a ball and that ball is white, the probability of us picking a white ball from a set of balls containing 11 balls, 8 white and 3 black, will be 8 over 11. And if we picked a black ball, the probability of us picking a black ball from that box will be 3 over 11. Now take note that once we pick the first ball, that ball is not replaced back in the box. So if we have already picked, it means now we are remaining with 10 balls because one has already been picked. So the probability of us picking the white ball, given that the first ball was white, will be 7 over 10. Because we've already picked one white ball, what you are remaining with are 7 white balls. So the probability of us picking the second ball to be white will be 7 over 10. And the probability of us picking the second ball to be black, given that the first one was white, will be 3 over 10. Now here, the balls have reduced, they are 10 in total, but take note, we first picked the white ball. So the black balls at this point are not yet affected. What reduces is the number of white balls because the first ball was white. So the second ball therefore will be out of, if it's black, the second ball will be picked out of the 3 black balls, but from the total of 10 balls in the box. So the probability of picking a second ball to be black, given that the first one was white, is 3 over 10. On the other part here, If the first ball was black and then we pick the second ball to be white, remember, once the black ball has been picked from the box, the total number of balls in the box will reduce to 10. So the probability of us picking a white ball, the white balls are still 8 because what we picked first was a black ball. So the probability will be 8 over 10 because the total number has reduced. But for the black balls, because the first one was black, it means the black balls are now 2. So the probability of us picking a black ball will be 2 over 10. Let's put this information in the equations and then we solve so that we get the probability. So probability of different colors is probability that you picked white and then black plus the probability that you picked black and then white. Putting in the probabilities, the probability that the first ball is white is 8 over 11, and the probability that the second ball, the first ball is black. Okay, so here we're looking at different colors. So white, black. So the probability that the first ball is white is 8 over 11, and the probability that the second ball is black, given that the first ball was white, is 3 over 10. Plus, we now want to get the probability that the first is black, second is white. The probability that the first ball is black is 3 over 11 multiplied by the probability that the second ball is white given that the first ball was black. So this will be 8 over 10. Simplifying this will give us 24 over 110 plus 24 over 110, which is 48 over 110, or simplified to 24 over 55. Let's look at part 2 of this question. So part 2 now is a situation where we want to find the probability that they are of the same color. Same color, we are looking at white, white, and black, black. Okay, so white, white, or black, black, which means we are looking at probability of white, white, plus probability of black, black. Putting these probabilities in this equation, what we know is that if you pick the first ball to be white, the probability will be 8 over 11. And the probability of you picking the second ball to be white, given that the first one was white, is 7 over 10. Because once you pick the first ball, the number of white balls will reduce to 7, and the total number of balls will reduce to 10. So white ball second, given the first was white, is 7 over 10. And the probability of us first picking a black ball is 3 over 11. The probability that the second ball is black, given that the first one was black, is 2 over 10, or 2 divided by 10. Simplifying this part here, 8 over 11 times 7 over 10 will be 56 over 110. And 3 over 11 times 2 over 10 will give us 6 over 110. This if we sum up the two, we will have 62 over 110. And this will be equal to 31 over 55 in the to the lowest fraction. Okay, let's look at task number 2. The second task we have is that a 4-digit number is formed by randomly selecting and arranging 4 digits from the numbers 1, 2, 3, 4, 5, 6, and 7 without replacement. Find the probability that the number formed is number 1, even, and number 2, over 3,000. So we want to form a 4-digit number from a set of these 7 numbers, from 1 all the way up to 7. Now, if we are to pick the number, we are told that we need to ensure in the first part that that 4-digit number formed is even. And then in part B, we need to ensure that that number that has been formed is over 3,000. To begin solving this question, let's first allow E to be the event that the digit is even. Then what we are required to do is to find the probability of E. So probability of E will be equal to the ratio of the total number of observations that are even divided by the total number of observations in the sample space. Now we note that in the sample space we have 1, 2, 3, 4, 5, 6, and 7. Now what we are doing here, we are conscious because we are told that we need a 4-digit number. Therefore, we need to first pick numbers that are even from this set, and then also fixed numbers that are in the sample space, but they should be 4. So we pick from the largest, coming all the way down until we have 4-digit numbers. Now what we are asking ourselves is, in how many ways can we select such a number? Okay, so let's start by first finding the number of observations that are even. In how many ways can we pick observations that are even? So let's draw, let's put some dashes here, and then we fill in the values, or we put in the required values. For this number formed to be even, the last number must be even. So regardless of which number will be picked, what we want is to ensure that the number that we are going to form must be even, and we're talking about a 4-digit number formed from a set of numbers from 1 to 7. So therefore, the last digit here must be even for these numbers formed to be even. So we are saying, in how many ways then can we select an even number from this set? If you check, we have 2, 4, and 6. So there are only 3 even numbers in this set. So therefore, our last digit here, we are saying we can actually arrange the even number or pick an even number in 3 ways. So we put the 3 there. The remaining numbers, once you move out, you pick any one of the even numbers, what you remain with are 6 digits, because we are sampling, or we are selecting without replacement. So once one way has been used, you fish out an even number, you remain with 6 digits. So therefore, the remaining of the numbers can be arranged in 6 ways. Once you pick this one number again, what you remain with will be 5. The remaining numbers will be picked from 5, and the remaining number will be picked from the 4. So therefore, what we need then is to multiply these numbers. So we are saying 6 times 5 times 4 times 3. This will give us a number of ways of selecting an even number from that set. We also need to get a number of ways of selecting from the sample space 4 digits. So what we are saying is, again, we need to have the dashes and fix the values. Now from the sample space, we have 7 elements or 7 numbers. And therefore, for us to pick the first one, we'll pick the first one out of the 7 numbers that we have. So the first one we picked from the 7. The second digit will be picked from the remaining 6. The third digit will be picked from the remaining 5. And the fourth will be picked from the remaining 4. Again, we multiply these numbers so that we get the total number of ways of selecting or arranging the numbers in the sample space. From these, then we can now put in these values in our formula. So NA is 6 times 5 times 4 times 3, and NS is 7 times 6 times 5 times 4. When we simplify this, what we will end up with is 3 over 7. Therefore, if a 4-digit number is to be formed by randomly selecting and arranging the numbers 1, 2, 3, 4, 5, 6, and 7 without replacement, then the probability that that number formed is even is 3 over 7. Let's look at the part B. So part B wants us to find the probability that the number formed is over 3,000. Now take note again here, for the number to be over 3,000, it means the first digit must be 3 or more. Okay, so therefore we're saying let A be the event that the digit formed is over 3,000. Then the probability of A will be equal to number of ways of picking a number that is over 3,000 divided by the number of ways of picking 4 digits from the sample space. So again, let's start with NA. So we put the dashes there and then we start picking the values. First, we are concerned with numbers that are over 3,000, meaning the first digit here must be 3 and above for this 4-digit number to be over 3,000. So now, when we go to our sample space, how many numbers are 3 or more? We see we have 1, 2, 3, 4, 5. So there are 5 numbers that are 3 or more. Therefore, the first number here can be selected out of those 5 numbers. Once you pick out the 1 from those 5, the rest of the numbers now, including 1 and 2, can be selected from the remaining 6 numbers. So we have now, next will be 6. The other digit will be picked out of the remaining 5. The other digit will be picked out of the remaining 4. Then we multiply these numbers to get the number of ways of picking a number that is 3,000 and above. Okay, I mean the number that should be over 3,000. Then for the sample space, as earlier, the way we did it earlier, we said we have 7 digits. So the first digit will be picked out of the 7. The second digit will be picked out of the 6. The third digit will be picked out of the 5, and the fourth digit will be picked out of the 4. Therefore, if we multiply these and put them in our formula, what we will get to be the probability is 5 over 7. So we can change this E must be A, so probability of A. So even here, this should be A. Okay, let's do that together. So we're saying this is A, and this is A. So we are finding the probability that the number formed is over 3,000, and we said let A be the event that the digit formed is over 3,000. That probability is 5 over 7. Let's look at the third task before we wind up with permutations. If the letters of the word minimum are arranged in a line at random, what is the probability that the 3 M's are together at the beginning of the arrangement? What is the probability that the first letter is I and the last letter is also I? And finally, what is the probability that the 3 M's are together? Now, when you look at this question, it is a question from permutations. And for us to be able to work this one out, we need to remember the rules of permutations. So let's start by finding the probability that the 3 M's are together at the beginning of the arrangement. Okay, so let A be the event that the 3 M's are together in the beginning of the arrangement. If this is the case, then we're saying probability of A will be equal to number of ways of observing 3 M's together at the beginning multiplied by the number of ways in which we can arrange the remaining numbers or letters in the sample space. For us to know NA, we need again to come up with the dashes. So let's start from there. So we know that this is 4 factorial over 2 factorial. Because if the 3 M's are together in the beginning, then we're saying we are fixing the M's. And these M's, once you fix them, they can only be arranged in one way. Because they will be placed at in the beginning of the arrangement, they will not move to any other part. So the M's will be fixed, and it's only in one way that we can do that. Now, once we remove the three m's and we put them here, what is remaining is I, N, I, and U. So we are then remaining with 4 letters. Since the three m's have been placed in the beginning, the remaining 4 letters can now be arranged in number. The first one can be arranged, the first letter will be 4 out of the 4, the other one will be out of the 3, the other one will be out of the 2, and the last one will be out of 1 since it's alone, since it is the remaining digit. But take note that we have letters that are replacing, that are repeating here. For example, I and M are alike. So because the M's are already fixed at the beginning, we are concerned with the I's. The I's are identical, so what we are dividing this with is a number of ways. Remember, we said that if we have elements that are alike, then we divide the NA divided by the total number of observations that are alike. So we say, in this case, we said P factorial. So we are saying, therefore, this will be 2 times 1, because only 2 letters are alike, which is the 2 factorial. So the 4 factorial is 4 times 3 times 2 times 1, and the 2 factorial is 2 times 1. So let's put these together. So remember, for the sample space in general, what we have is n factorial divided by p factorial multiplied by q factorial, where p factorial are elements that are alike, the first set that are alike. In this case, we have the m, and m, so meaning that our p factorial will be 3 factorial. And the q factorial is another set of elements that are alike from the set. Here we have I, so 2 i's, therefore q will be 2. So we are finding 7 factorial, which is the number of objects in this word minimum, divided by 3 factorial times 2 factorial, and this will give us 420. Putting these in the formula for probability, what we'll have is that probability that the 3 m's are together in the beginning of the arrangement will be 12 over 420. So this part here will give us 12. 4 times 3 times 2 times 1 will be, divided by 2 will be 12. And this part here, we found 420. Okay, let's move on to the second part. Okay, let's find the probability that the first letter is I and the last letter is also I. So if you see, we are fixing the first letter and we are fixing the last letter. So I at the beginning, I at the end. So we move out 2 letters here. What we remain with are 5 letters. So therefore, what we are finding is 5 factorial. But take note that 3 are repeating, are alike, M, M, M. Since the I's are fixed, the remaining 5, we're going to have 3 identical letters. So we are dividing 5 factorial by 3. Okay, so we'll have 5 factorial divided by 3 factorial. So here we are letting B to be the event that the first letter is I and the last letter is I. So probability of us observing the first letter being I and the last letter being I will be NB over NS. Now our NB, we're saying is 5 factorial divided by 3 factorial. To show how we are coming to this, let's have the dash, put the dashes and then demarcate. So we know the first letter must be I and the last letter must be I. And if we are fixing these letters, then each of the letters can only be arranged in one way. So we are putting 1 there and 1 at the far end. Now let's talk about the remaining 5 letters. We will have M, N, M, U, M. So we have M, N, M, U, M. Now, in how many ways can we arrange those M, N, M, U, M? What we will have is that there are 5. So we're saying 5 factorial divided by 3 factorial. Now 5 factorial in that, if you look at these numbers, since they are 5, when we select the first one and place it, it will be picked out of the 5. What remains are 4. So you select the second one, it will be out of the 4, out of the 3, out of the 2, and finally out of 1. Then we multiply these numbers. Now, because 3 of the remaining letters are alike, that is M, M, and M, we are then dividing this by 3 factorial. So 3 times 2 times 1. Again, we go to the sample space. We note that NS is N factorial divided by P factorial times Q factorial. And we noted earlier from our previous solution that NS is 420. So if we put these in our formulas, what we'll have is probability that the first letter is I and the last letter is I is 20 divided by 420, which will reduce to 1 over 21. Let's find solve the last one. We're saying what is the probability that the 3 M's are together? Now, if the 3 M's are together, all we are concerned about here is these 3 M's being together. So they can be together in the beginning, second spot, third spot, fourth, fifth, and so on. All we want is these 3 M's must be put together. So if we do that, let's let C to be the event that the 3 M's are together. Then the probability of C will be equal to NC divided by NS. Let's find our NC. We are going to put the dashes here again. So here we're saying it will be 5 factorial over 2 factorial, and let's show how that will be. We have 7 letters here. If you get M and M and M and put them together, they form 1. Meaning we start with the M's 1, 2, 3, 4, and 5. So we have M, I, N, I, U. Because the M's are together. So we are going to have 5 letters of which we need now to arrange these letters. Okay, so we're saying if the M's are together, because they will now be moving, it means we have another set of 5. Let's look at that. So we're saying M, M, and M. For them to be together, we bunch them. We put them like that. So these M's will be moving together, and then we continue I, N, I, U. These are the letters that we'll have. So if we count, we'll have 1, 2, 3, 4, 5. Therefore, we can arrange these in 5 ways. So, we can arrange these by picking first out of 5, second out of 4, out of 3, out of 2, and finally out of 1. So therefore, we are saying if we put these here, we'll have 5, then the other one we picked out of 4, the other one out of 3, the other one out of 2, and the last one out of 1. Then we multiply this. So that's 5 factorial. 5 times 4 times 3 times 2 times 1. Then because we noted that if the 3 M's are put together, they form like one letter. But we have the I's which are alike. So 2 letters then are alike. So we're going to have divided by 2 factorial, which is 2 times 1. For our NS, we still maintain the 420 because nothing has changed. And if we get this information and put in our formula, our probability that the 3 M's are together will be 60 over 420, which will then reduce to 1 over 7. Okay, so thank you very much for watching this video. If you have questions or comments, you can send us a WhatsApp message using the number that is showing, or give us a phone call, or better still, you can send an email to admin@imasori.com. In case you want to visit our offices, you can visit us at plot number 10424/10 Casanova near Charleston in Lusaka. I'll see you in the next video where I'll continue with counting techniques, and in the next video we are going to look at combinations. See you.